All right, here's 8-5, day number 1. We're going to, don't be intimidated by the title here, solving more difficult trig equations. It's really solving some different trig equations. We've solved plenty, and to be honest with you, the ones we're going to look at in 8-5, I don't actually think they're harder. This is taking the same language that the book uses. It calls them more difficult. You be the judge of that, but don't think too much of it. I'm just using the same terminology to be consistent, but I don't think they're harder. To be honest, I think they're different, but some of them are easier than what we've seen. We look at 8-5 after we do the trig identities, because some of the equations that we'll do will now involve some of the identities. Quick refresher, don't totally forget about the unit circle. Okay, just to go through these, at 30 degrees, it's always worth reminding ourselves that the sine is a half. That's the y-coordinate. Cosine is square root 3 over 2. And tangent, remember that one's not listed, but we can get that if we look at y over x. Multiply by the reciprocal, we get 1 over square root 3, which is square root 3 over 3. Okay, so if that number is not looking super familiar, that's where we would get it from, even though it's not on the unit circle. 45 is that special little angle. It has the same cosine as sine value, and that would make tangent 1. And of course, at 60 degrees, cosine switches with sine, and this just ends up becoming the square root of 3. Okay? Don't forget about those. Anytime we can go to the unit circle and get exact answers, we'd like to do that. Some of you have seen in our last checkpoint quiz that you would have lost some points on the test had you done what you did, because you kind of proceeded and used the calculator to get an approximation, which isn't wrong, it's just not as good as having the exact answers. Up here, let's do a little review first off with some identities. I always think it's nice to practice those a little bit. If you want to pause here and take a look at this review, certainly feel free to do that. If not, just stay with me. To simplify this, I would use a quotient identity, which is to write cotangent as a quotient. We can write it as cosine over sine. These are just two relatively simple ones that aren't particularly long. We've seen in 8.4, we saw some identities that took 5 to 8 steps, and it's worth noting, those are tough. That's some of the toughest stuff we've done all year, and some of you, a lot of you, have done a really, really great job in class working with those. The sines cancel. That simplifies to just cosine of y. On number 2, okay, we can use a little identity there. We should see the pattern here that we have cotangent squared and cosecant, which ideally should make you think of some of those Pythagorean identities. Let's leave cotangent squared of x minus cosecant can be taken out and replaced with 1 plus cotangent squared. Then we can distribute this negative sign and get rid of the parentheses, have minus 1 minus cotangent squared. Those cancel out, and look what's left. That actually simplifies to a constant, interestingly enough. That equals negative 1. That would mean no matter what angle we put in for x, cotangent squared minus cosecant squared, always going to be negative 1. All right? Before we get to 2 more examples with solving, one thing that's good to know. When simplifying trig expressions, okay, and this is primarily what we did in 8.4, it's legal, meaning you can do it. It's a valid step to cancel from the top to bottom when reducing fractions. It's kind of like dividing, okay? You can divide by a trig function. When solving trig equations, it is not allowed. Okay? It is not allowed. It's not that it's necessarily wrong. It's that a lot of the problems, like we've seen when we're solving, have multiple solutions. And if you divide by a trig function, when we get to an example, I'll show you what I'm talking about. You will lose solutions. You won't get all of them. Okay, bottom line, if you ever find yourself dividing by a trig function, don't do it when you're solving. All right, so here's a difference. This is telling us to solve 3 and 4 from 0 to 360 degrees. So we'll work in degrees here. The difference here is we have sine squared of theta. We haven't seen one like that. We haven't seen anything like that. So let's get going. You'll see some similarities from other ones that we've solved. For example, adding 1 gives us 2 sine squared of theta equals 1. Divide by 2, and that gives us sine squared of theta is a half. And at this point, I would go ahead and take the square root, and I would have that left side all the way down to just sine of theta, and this is the point I'll be able to use my inverse. Okay. Now I got to clean up this right side a little bit. It needs to be simplified. Think of this as just taking the square root of the top over the square root of the bottom. Square root of 1 is 1. Square root of 2 is not a perfect square, so we'll just leave it. But then let's go ahead and rationalize that denominator. And we get square root of 2 over 2, and I almost forgot. This is a really important thing. When we took the square root, don't forget, this is plus or minus. That should be the case all the way through here. Positive square root 2 over 2 or negative. All right? Remember, when we take a square root, we can get the two different answers, the value of each one, just the opposite sign. So what I have here is the sine of theta is plus or minus square root 2 over 2. Okay? Where we find ourselves here is, do we go to the calculator? Do we go to the unit circle? That all depends. Is this a sine value that we commonly see in the unit circle? The answer is yes. Square root 2 over 2 and negative square root 2 over 2 are on there. So at this point, I'd refer to it. You may want to do that now and maybe take a minute. See, if you have a unit circle handy, refer to it. See if you can get all the solutions. I'm not going to tell you right now how many there are. But pause here if you want and see if you could refer to that circle and get all of them. Okay, so we're looking at the y-coordinate because this is sine. At 45 degrees, and remember, here we're solving in degrees. That was what told us that. 45 degrees has a sine value of square root 2 over 2. 135 degrees has a sine value of square root 2 over 2. Did you get those? 225 degrees has a sine value of negative square root 2 over 2. There's solution number 3. And 315 degrees has a sine value of negative square root 2 over 2. So there's 4. Notice that all solutions are between 0 and 360, and they all have sine values of square root 2 over 2 or negative square root 2 over 2, and we refer to the unit circle. Okay? Let's take a look at one more. Number 4. We're still solving on the same interval. Okay, so we're still going to look at theta from 0 to 360. Now, this one's a little bit different. It's got a squared term, but it also has just a regular cosine to the first power. That would be this term right here. Okay, this one's a little bit different. How do we handle this? Well, if we take a really close look at it, it looks like a structure that we've seen before. It kind of looks like x squared minus 3x minus 4. Okay? Like a quadratic. It's pretty darn similar to that. Okay, so we actually handle this case very similar to how we would handle a quadratic. We would try to factor it first. So right now, I'm kind of just pretending the cosine piece isn't there and thinking about factoring x squared minus 3x minus 4. Lead coefficient is 1, so I'm just looking for two factors of negative 4 that add up to negative 3. And negative 4 and positive 1 will do the trick. Okay? So now going back to cosine, let's just write it the exact same way, but where we see x, replace that with cosine of theta. So I could factor this with cosine of theta minus 4 times cosine of theta plus 1. Okay? If I were to FOIL that expression, it would take me right back to the expression that I started with. At the beginning of this lesson, when I gave you that little warning about dividing, this is what we're talking about. Okay? It would be tempting to maybe divide each side by... I'm gonna write it out here. I'm gonna put it in red so you know that this is totally wrong. Don't do it. Divide by cosine of theta minus 4. Divide by cosine of theta minus 4. Cancels. And we'd be left with cosine of theta plus 1 equals 0. Okay. I'm now backtracking. That's all the incorrect work I can stand for one lesson. That's what we're talking about. Don't divide by each one of these factors, okay? Because they both potentially contain solutions. We're not guaranteed that both do, but they both could, and doing that could result in us missing solutions. Instead, split up the two factors. Cosine of theta minus 4 equals 0, and we have cosine of theta plus 1 equals 0. And now we can continue to solve each of these. That would be to the point where I could take the inverse. And that would be to the point that I could take the inverse. Okay? Cosine of theta equals 4. 4 is not a cosine value you'll find on the unit circle. As a matter of fact, it doesn't look like a cosine value we've ever seen before. It's larger than 1, so when you take the inverse, you will get an error. So from that factor, we don't get any solutions. Okay? We'll see examples where both factors do give us solutions, but it just works out on this one that the first one doesn't. Factor number 2 has been solved to be cosine of theta equals negative 1. Negative 1 does remind us of a cosine value on the unit circle. Cosine is negative 1 at 180 degrees, and here's a rare case. Typically, when we have a trig equation like this, we get two solutions off of the unit circle. Because we're all the way over on the left side, 180 degrees is actually the only angle on the unit circle that has a cosine value of negative 1. That's the only solution from 0 to 360. If we were to look at coterminals, we'd come back to more solutions, and we get those by adding or subtracting 360. But this problem only said to get the solutions from 0 to 360 degrees. So that's it. 180 degrees is the only angle we could plug in for theta if we plug that back to our original equation to get 0. All right. Hopefully those two examples help. We will spend a second day on 8.5, but those are two good examples with some trig functions that are squared that are a little bit more like what we'll see in the rest of 8.5.